Hello everyone, welcome to Automotive World. I'm Martin Carl, I'm the editor of Automotive World. I'll be moderating today's session, which is all about battery development for electric vehicles and how they can be optimized not only for vehicles but also for stationary applications. We're going to be hearing from experts from FEV's EVA Fahrzeugtechnik today, who will be discussing the development of battery storage systems for EVs and stationary applications. A little bit of background: the batteries used to power EVs can also be repurposed, but they need to be optimized for any use case in question. For the next hour or so, we're going to hear insights into the development of battery energy storage systems for EVs and various stationary applications from our experts from EVA. So I'm delighted to be joined by Marco Moscariello, who's head of product development, and Jürgen Kölsch, research battery technician at EVA Fahrzeugtechnik. Topics today will include battery system development, including the design, hardware, functional development and servicing of batteries. We'll also hear about second life EV batteries in stationary applications, DC quick charge stations for EVs, and power grid stabilization. We'll have a presentation followed by a Q&A. If you'd like to ask any questions, please type them into the Q&A box on your screen. And as usual, slides and a recording of the event will be made available afterwards, and we'll send you an email to let you know how and when you can access those. For now, though, I'm going to hand over to Marco and Jürgen for a presentation entitled Optimizing Battery Development for Electric Vehicles and Stationary Applications. The floor's yours.
So welcome, ladies and gentlemen, for the webinar. Thank you for joining us. Before beginning, I want to have a look on our agenda. Before introducing ourselves, we're going to have a short company profile, and then we will pass, after the introduction, to all the important things that you have to take care of while using a vehicle battery for a stationary application, and at least, like already said, the question and answers. So before starting with the company profile, we will have a short introduction. I give to Jürgen.
Here, Jürgen Kölsch. On the left-hand side, I'm since 2004, 14 years at EVA Fahrzeugtechnik at research and development new technologies. I'm supporting OEM projects in the field of electromobility like inductive charging, solar charging, and at the moment all solid-state lithium batteries. So I give back to Marco.
So I want to introduce myself, Marco Moscariello, my name. Since 2008, I'm working in the product development at EVA, and since 2014, I'm director of product development and also responsible for the sector stationary battery systems. So what's behind EVA? We were founded in 1994 in Munich. Our headquarters and our branch offices are also in Munich. We're working on a project with more than 300 talents, and since last year we are a proud member of the FEV group, so maybe also well known for you. So just for you to give you a good overview, what are the main topics where we're working on in our company? So one topic is the battery, from the cell module onto the battery pack and even the stationary battery systems, from the early concept phase to the project management, until the test management, even the problem management. This is what we do for the battery systems, for automotive and stationary application. We do as well for the traction motors, for the hybrid and BEV vehicles. And to let work everything good together, we also do the calibration and integration of the driving train and even the user interface. Another important thing is our project and fleet management. So for you, what does it mean? We build the interface between the product line and different development departments while managing the service station, the hardware and software upgrades, the planning of the cars. We even do the quality management for interior and exterior, and the testing management for interior and exterior parts. Last but not least, we've got our own production in Munich. We began with roof racks, auxiliary headlamps, and hardtop racks, and right now we are planning to do some prototyping for batteries and traction motors. So I will give the word to Jürgen for doing the introduction. Thank you.
So introduction, why are batteries, stationary batteries, so important? So we think measures to counter climate change are leading to more and more renewable energies in the power grid. And also the demand for energy storage system is increasing worldwide, and the market system is emerging. The development of high voltage batteries requires various aspects, mobile and stationary systems. And in our presentation, we would like now to explain these differences to you in more detail. First of all, the Ragone plot, you see at the x-axis the energy at cell level at watt-hours per kilogram, and on the y-axis the gravimetric power density at cell level watt per kilogram. So x is range, and the other is when you want to accelerate with electric car. So my first electric car I bought 2001 with lead acid batteries, and as you can imagine, it was not so good idea in winter time. 25 kilometers, normally 30 to 50 kilometers. Nowadays we have different battery technologies now up to lithium technology. And recently I work at an all-solid-state battery project, and we want to break this 200 watt-hours per kilogram. So I'm at the right-hand side here of the diagram. But there are batteries for 2030 or so, as not recently battery technology, but we're working also on this technology for the future. So the next topic, operation strategies. So here in the middle you see smart grid, and the best for smart grid is to couple it with stationary energy storage. A combination for photovoltaic system and home storage is widely used today. It's a good combination. The other is combining the heat and power units or possible small wind turbines, also interesting. Monetary incentive exists through the use of self-produced electricity. Less electricity has to be extracted from the grid. And in Germany you got 12 euro cent when you sell this photovoltaic electricity out of your household, and you had to pay 28 cents per kilowatt hour. So if you want to charge an electric vehicle, it's a good idea to couple this photovoltaic with small electricity storage, and you can charge the electric car with 12 cents. And at the left-hand side, you see here for smaller villages, you can be largely self-sufficient by using this photovoltaic system or wind turbines with this buffer storage systems. And also it's increased acceptance among the citizens for wind turbines, and excess energy, it can be fed back into the system, creating a new source of income. On the other hand, it's participation in the energy market. Now it's the big systems. You can supply on primary or secondary balancing power, also on minutes reserve or temporary. Benefits are contribution to the voltage and frequency stability here in Europe, 50 Hertz. And for companies, also it's possible to make peak shaving, so peak load reduction. And in emergency case, blackout, you have the possibility that this battery can help the power plants to start again and to continue the grid again. So buffer storage, excess energy from photovoltaic, wind, biogas can all be stored, and it's a good basis for sustainable power supply. So here, emergency power, UPS, so far often been implemented by lead-acid batteries. Where this disadvantage from the Ragone plot is here. Nevertheless, it's a good technology. Lead batteries, but are a logical alternative in the face of an immediate ban on lead. It's toxic, so there is a ban in Europe, and existing systems designed for lead-acid batteries can be also particularly taken over. Due to the possibility of slow recharge after use, there is hardly any influence on the service life, so that the systems can be used for a long time. The next is the development of standalone systems, so off-grid, smart grid. And here in areas where continuous supply of electricity cannot yet be guaranteed, off-grid systems can help, like developing countries, remote mountain huts, etc. Battery storage can also help where the infrastructure is weak. In the picture you see fast charging stations, so with smart grid systems, vehicle can feed unneeded energy to charge it in very small time into existing battery systems in order to intercept power spikes in a targeted manner. And the required energy can then be recharged. So if you have a small grid, you can buffer this power station with these batteries. So next topic is this grid integration, very interesting. Use of fully developed and protected vehicles, high voltage batteries, and it's also possible, you see here battery chain from us for first or second life. You can integrate it in the power grid via this bidirectional inverter. So AC-DC converter here is only optional. And in the IT network with galvanically isolated network, this application corresponds to the application in the vehicle. So the architecture continues to feature first-hour security. Installation monitoring is required for this purpose. But if you have a TNS network without a galvanic isolation, you have no first-hour security, and you have to choose a better security device. So there are two different connections for the high voltage battery. Here on this slide, this is this parallel connection. So vehicles are not designed with vehicle batteries for this parallel operation. So in parallel interconnection of several high voltage batteries places additionally demands on the system architecture. So the battery with the highest internal resistance make the smallest contribution to the power output. It's the same as the baddest cell in the module, but here it's from the whole battery point of view. Then balancing is also interesting. So normally when you drive an electric car, you drive 1 hour per day. A stationary plant operates 24 hours. So at cell level is often implemented in the vehicle, and at high voltage battery level, this may additionally be required in the stationary battery depending on operational requirements. And the DC intermediate circuit can no longer be disconnected from these individual batteries, and the balancing currents must be taken into account. It's very important. So next slide is the serial connection. The vehicle high voltage battery usually uses 400 volt. There are several OEMs with 800 volt, but for normally it's 400 volt. For cost reasons, over dimensioning is avoided. So normally the range is from 450 to 500 volt. And serial connection of several high voltage batteries therefore often poses a problem for individual components. So there are many questions like, can contactors safely disconnected even under higher voltages, or from the isolation measurement device concept designed to double or triple voltage, and air and leakage pathways also sufficient for higher voltage.
Okay, so now we're gonna pass to the isolation concept, which is quite interesting. So what are the challenges? Just one example, as already explained, the vehicle high voltage batteries are normally designed for 400 voltage range, and operating voltage of the components is something about 450 volts to 500 volts. The thing is that for stationary application, normally you often have serial connection of several high voltage batteries because it's necessary in order to achieve the common voltage interface that is more between 800 up to 1200 voltage for stationary applications. So this has a big benefit. It means that higher voltage means a lower current for the same power, and so you can use a thinner cross section, which has a big impact on the costs and on maybe also on the service concept. So let's have a look. What can you do with the isolation? There's one solution. The isolation concept must be considered separately and re-evaluated. This is quite easy to understand. You cannot use it because of the different voltage range, and there's one solution. You can make the installation of the high voltage battery. Maybe you can install it in a isolation. So for this purpose, the high voltage battery housing must not be earthed. But on the other hand, with this variant, there are potentials against earth that can form on the high voltage battery housing. So this means you have to consider this in the whole isolation and safety concept. So far from the isolation concept. Now we get to the cooling concept. There are two different methods. You can go with a passive cooling or with an active cooling. So the passive cooling, you first, in order to dissipate heat loss, a cooling concept is necessary. So on the one or the other hand, you have to make sure how the system has to run and how are the circumstances, and it's possibly how it's set to cool them actively or passively. So it has to be cooled to avoid thermal degradation, because with this, not the fully power can be provided anymore. So this should be one of the most important things to take care while designing the battery for stationary battery applications. Then, in order to warm the batteries at cold temperatures, which is quite necessary, it is possible to heat them either with the electricity or with coolant. This would be more actively shown on the other slide. It's important to warm them because it's necessary, especially here in Germany in the winter, or depends where you put the stationary battery system. It's required because the battery don't like it to be under zero degrees, because charging the cells is particularly damaging. And to have a safe operation level, you have to make sure that you have the right temperature level at every time. So with the passive cooling, the thing is that you can connect to large thermal masses, for example, the housing. This can be an advantage. This is something that you have to take care of. You have another advantage that no active components for especially, for example, pumps or compressor fans are required, which has another impact on the costs. Even wind flowing through the battery without fans is also considering as a passive cooling. So there's no system interface from the vehicle that you have to serve. So it makes it on this hand more easily to handle, but on the other hand, you have got only moderating cooling capacity. So this means that this system, passive cooling, depends a lot of the ambient temperature and the circumstances around the battery rack. Let's have a look to the active cooling. The active cooling, you have got the big advantage that you can actively switch it on and off like it's required. So this is a big advantage. It depends on how you realize it, or if you realize it with fans or with coolant, but it doesn't matter how, you need additional components. This means, for example, you need fans, you need compressors, as well as coolant or refrigerant. This is something that you have to consider in the early concept phase and in design of the battery system. If you want to use a plug and play from the vehicle, you normally have a complex system behavior, because in the vehicle it is inserted in the existing circuit of the vehicle, and this has to be designed accordingly for your stationary application. This means it has another impact on the cost level. But on the other hand, you have got very high cooling capacity, even if you have high temperatures outside. So maybe you put more intelligent and more effort into the active cooling concept, and you have less circumstances or less things you have to take care of around the battery pack. If coolant is used, is it even possibly to heat the battery, which is, like I said before, a big advantage in winter time, because you have to take care that the battery has always, let me say, the perfect temperature to operate. If you have an active cooling, the valves are, for example, you have to control them. You have maybe to make a special diagnostic to see if they work properly or if they have any error, because this can have an impact on the active cooling concept. So if you design a cooling system in the vehicle, it is specially designed for a lot of dynamic, for you brake, you accelerate. For stationary application, it's more permanent. So you have to take a look if it works, if it can work maybe for 24/7 or for longer ranges. So this is something that you have to take care of if you want to use a plug and play, for example. If you have coolant, you also have to take care of for your service concept, because it has to be regular. You have to do regular checks if the fill level is okay, because if not, maybe you can go into other problems that it do not work properly, and your cooling capacity is not that what you have designed for. And another important thing is, even not only for the design phase but also for the service phase, that if you have any leakage of the coolant, it can cause any battery damage, for example, short circuit or corrosion. So this is something that you have to take care of if you really need a passive or active cooling. So let's go to the battery management. Like I say, the heart of the battery rack. So some words to the software development process. So normally you've got the requirements, and from that one you go to the functional order, the concept, the functional requirements, until you reach to a functional model and you get to the software themselves. Once you've got the software, you have to do the functional test. You can do that, for example, at the hill, hardware in the loop, and but even at the test bench, until you reach to a vehicle integration, or even a stationary battery integration. It's not really different. And then you have to take care that you normally lead a lot of loops to the problem management to see what has to be adapted to make the software run properly. So this is just for you the procedure for the software development. Let's have a deeper look to some software features. The balancing. The balancing in the car, it's quite easy, not easy to realize, but it's easy to say when it has to work. It has to work maybe when the vehicle is not in operation. So this is quite easy, because normally a vehicle, if it's not a sharing drive, it's working only about 5 to 10% a day. The high voltage contactors normally open and the vehicle is in sleeping mode. This is what I say, it's quite easy, because the operation strategy of a vehicle, it's quite easy to manage. But for the stationary applications, it's a little bit different, because you've got some problems with this. The battery is mostly in operation, or let me say it's not sleeping. So you need other basic conditions to set up a balancing. For example, when the cell is in a relaxing phase, maybe when the cell voltage are equal for X minutes, to maybe it makes sense to start a balancing, or if there's no current, this can also be an option where you can start a balancing. And for example, if you have got two battery racks or packs in series, it can be all cells have to be meshed equal and in a mesh, and the battery should take the smallest cell voltage in this mesh as minimal cell voltage for the balancing. So this means that the logic on how you do the balancing has to be adapted. So maybe you have to adapt some telegrams, but it's something that where you cannot use the vehicle software like a plug-and-play modus. Let's have a deeper look to the communication speed. So in the vehicle, you normally have a communication time on the CAN up to 20 milliseconds. It's extremely fast because you've got the dynamic driving profile. There's a fast reactivity on the functions such as current, voltage, or power limit. For the stationary applications, it's completely different because there's more in a second range, let me say, that it's not possible to react to the signal so fast or to react to changes so fast, but it's not even necessary. It has to be considered in a safety concept, but if you want the system to react too fast, maybe this can lead to an error. To the communication interface, there are some different, or let me say, some things that you have to take care of. In the vehicle, the CAN community, the CAN bus normally is very busy. There are a lot of data from all different interfaces provided from as many participants. So the use of several protocols like CAN, ODX, it depends always on the application, is necessary. For stationary application, you can go with another concept because only a handful of data is required for the for the stationary application to control the probably. So the CAN is less loaded. So several batteries can be connected to one CAN. This CAN has also an impact on the costs for sure. But you have to take care once you want to connect the batteries to one CAN. You have to look to the different IDs because you cannot have the same IDs on the same CAN. So maybe you have to adapt the software that it's able to be shared on one CAN. So this is quite an important thing that you don't have to forget. So if you want to use the automotive protocol, some protocols need specific software, for example, the ODX. So this means also higher costs. Maybe you can switch to standard protocols, for example, the Modbus. There's something that you have to take care of, or you have to look in the early concept phase how you want to realize it. Okay, so let's have a look to the safety concept. The safety concept itself, I think that you can talk about this for several weeks. We try to focus on the main topics. Let's have a look to the general safety concept for a stationary battery system. You have to do a risk assessment, and for that you need the stationary emission profile. What does it mean? That the stationary emission profile contains change requirements of the automotive battery to the stationary applications. For example, you've got service life, you've got performance, maybe environmental conditions, operational strategies. That's something that you have to take care of before looking deeper to the next steps. Once you have done this, you have to go to the mechanical safety, chemical safety, electrical safety. In the electrical safety, here it must be shown that all safety aspects like mechanical, chemical can deviate significantly from the actual vehicle applications. So due to a modified emission profile. This is what I said. At the emission profile, you have really to take care of, you have to put a lot of effort to see what is the main difference, which will change. And this has to be also adopted in the functional safety. We will show some other information on the next slides, the thermal safety and the organizational safety, until you reach the safety concept itself. So there is one important other thing you have to know, that normally you have to inform about residual risks. But it's important that residual risk may only be passed on the customer as a last resort. So normally you should try to avoid to pass any risk to customers. I know sometimes it's not possible. It depends on how the facility is used, if it's how the customer are, if they are well known about the systems, if are specialists or not. So this is something which is really important, because you have to do this in advance before passing through the whole safety concept. So as next step, I don't want to go deeper into all the different bullets, but just some difference between functional safety for the automotive and functional safety for the stationary application. So the automotive functional safety is normally developed according to ISO 26262, comparing to the stationary applications, which are developed according to IEC 61508. So looking on the left side for the automotive, normally you've got an item definition. You have to do clear the hazard analysis and risk assessment, and then you have to do a RCL determination. What does it mean? In the vehicle, functions are considered like sensors, logical, and actuators are evaluated according to RCL, Automotive Safety Integrity Level. This is one of the main difference, because in industrial machines and plants, like for stationary battery systems, functions are evaluated according to SIL. This means Safety Integrated Level. So there are translation tables for this purpose, but these cannot only be used, they can only be used to a limited extent. So that means that you have to do a complete reassessment of the respective functions if it's really correct. So this means a lot of effort. After the RCL on the left side, you do the functional safety concept like explained, and then you have got technical safety concept divided in software and hardware until you reach the integration and the test and the approval. On the right side, it's similar. You have the safety planning, development, and safety assessment. You also have to identify the hazards and to do the assessed risk. This means that you've got severity, frequency, and tolerability, what you have to take care of, and then you've got a loop that you say, can I mitigate the risks, or do I have to assess residual risks? And this is something that you have to do until you reach the functional safety concept. So this so far for the functional safety. Let's go to the next step. It's the declaration of conformity. That's always from our project that we've seen. It's quite really important topic, because you always focus on the operation strategies, isolation concepts, the battery management, safety, all the technical aspects. But one thing that you have to do also with the first steps is to say, okay, what declaration of conformity, what laws do I have to take care of, what directives are really applicable for my application. So it's quite important, and we want just to give you a short introduction. This is also something where you can have our own webinar on it, but just for you to have a good overview. So from the vehicle battery without CE to the CE certification, so what has to be done? So there's the obligation to affix the CE marking according to the common legal framework for the marketing of the products. The CE marking is obligation for all the products that falls under this law regulation. So that it is not a nice to have that you say, okay, I can apply it, but I don't want to. So it's quite clear, if you fall under this harmonization law regulation, you have to do this. Another thing is, which is different between using a stationary battery system or a vehicle battery, is that the low voltage and EMC directives are applied to battery storage systems, and the machinery directive is excluded for passenger cars. So this means you have a gap between the different directives that has to be applied on each battery pack. So this means you have to take care of before beginning development. What does it mean? What does it mean for the development, for the safety concept, and so on? So this is because I say it's important to have a look before beginning work. And then, like I said before, there's an obligation to apply the CE marking if you fell under this regulation. On the other hand, if you do not fall under this regulation, it's misused to affix a CE marking. So I cannot say it too often. It's really important to have a look on this topic before beginning the development. Okay, like I said, there are different declarations or the different directives. I don't want to pass through them. Just one overview of this too. The machinery directive is it's important. The motor vehicles and their trailers covered by council directives, they do not fall under this scope. So this is important for stationary applications, but not for automotive. And the low voltage directives, they say that this should be applied to all electrical equipment designed for 500 to 10,000 volts for alternating current and 75 to 1,500 volts for directive current. So this is important that you have it in your scope and you know that you have to take care of them. So I said that the conformity, that the declaration of conformity is quite a complex process. So we just try to put all the different steps that you have to do on the following two slides. So let's have a short look on what you have to do on this topic. So the conformity assessment procedure must be carried out and documented. So this is most important. You have to really have a good documentation on what you have done, especially for the clarity of conformity. You have to have the hazard and risk analysis, like I said before, that must be carried out. You have to make sure that you have it done properly. So if it's complete or not, that's something that your experts have to had you prove, but it's important that you have it. And you also need a general description of your product. So if there are any drafts or manufacturing drawing diagrams of components, so on, you have to put it also inside. And if it's necessary for better understanding of the drawings or maybe of the plans of the operation of your product, you have to explain it. So it's not only done by putting the drawings to your declaration. Maybe if you have to do everything which is necessary to make it understand better. And there's a list of harmonized standards and technical specification that you have to take care of and that you have to apply full or in part. So you have also to describe how the solution has been adopted to meet the essential requirements. So this is something, if you do not apply them completely, or if you do not apply them, you also have to describe what have you done to meet the essential requirements. So you cannot say, okay, they have to be applied in full or in part. I do not reach their goal, so let me put them away and don't put it on the declaration. It's not so easy. If you don't put it on the declaration, you also have to describe which solution you have adopted to reach it. In case you have applied it only in part, you have to apply exactly the parts that you have applied on your declaration of conformity, so that everyone can see, okay, he has applied. If he don't have applied everything, he has applied this and this and this topics. Once you have done this, the results of the design calculation and inspections should be listed, and the inspection report must be created. So this is something that you have to have to get a conformity. And important that your technical documents should be kept for at least 10 years until the last placing on the market. So this does not mean that you have to take them, that you have them for 10 years after you placed them the first time, but after the last placing. So this is quite important that you keep them another 10 years. Then the exact contents are defined in the modules, and if applicable in the harmonized legislation. So if you look to them, there are all the different, all the exact contents that you need are explained there. So just follow the steps just to get the answer to the things that you have to do. So everything should be easy going. The operation instruction is quite important, not only to have a safe use, but it has to be part of the technical. It can be part of the technical documentation, but it has to been provided. So technical documentation, it's nothing without the operation instruction. So this means the operation instruction has to contain everything for a safe use of your product. And at least if you have passed all the different bullets successfully, you can put the CE declaration of conformity on your product. And if you follow this declaration, you have to put it. So now we're going to pass to the service concept.
So the last topic, service concept, you see here the production and logistic process in the vehicle supply chain and the spare part supply. So at the left-hand side, the cell production, and up the logistic cells to the module production. So before 2 years, you could fly with cells with high SOC levels, so state of charge levels. And then we reduced it that you aren't allowed to fly it above this 30% state of charge. And for many OEMs, it was a big problem. So afterwards, at the cell module production and afterwards at this high battery production, now you had to charge it, and it's difficult in this logistic pathway to make charge stations to put them to a higher state of charge level. To put it on 100% is not a good idea, so the batteries could be more damaged, and afterwards at the vehicle factory, the vehicle had to go worldwide to the customer. So there are many weeks to ship at heat, and afterwards, the customer want to get an electric car with good batteries and not empty batteries or damaged batteries. And afterwards, when he drives the car and a module is damaged or out of order, there was also another logistic for the replacement of a cell module. It's the same, so if you have much time, you can wait for the ship. And when you had to, this module very fast, you had to fly it, and the same, it's not allowed to fly it above this 30% state of charge. So afterwards, you had to charge it up and in this repair process. So this is normally from cell production left to the electric car at the right-hand side. And we can go now to this next slide. It's this repair process and spare parts supply using cell module replacement as an example. So this is example for the vehicle, but we did it also for our plants and stationary use. So if a module is damaged, we had a service concept, and it's like the same here at the vehicle. So at the left-hand side, a diagnostic. I have to look what had to be repaired. All modules. It's one module, and what position was this module. I have repair instructions, and afterwards I had to put the batteries out of the car. In stationary use, you have this chain, open the chain, put the module out. It's this partial disassembly of the vehicle and removal of the cell module. And now it's important to charge or discharge the module that it has the same state of charge level like the other modules. So you haven't filled it up or very empty module. And then assembly of a battery and installation of a cell module, the final test, and you can drive the vehicle again. So now we are at the end, so our summary. So first, in my introduction, You need climate change. For a few weeks, it was a climate change report. We had high demand for energy storage systems and different aspects for mobile and vehicle applications. And the second topic is operation strategies, off-grid, smart grid applications, emergency power units, opportunity for peak shaving, also combined with renewable energies, then grid integration with bidirectional power inverter for grid integration. Then there is isolation concept with 400 or 800 volt systems, different seepage and clearance distances, with active and passive concepts for the cooling. Then the heart of this four systems is battery management, the balancing, different communication structures. Then the safety, functional safety, all kinds of safety concepts. And at the end, declaration of conformity, very complex topic. And now at the end, our service concept.
So now we reach to the end, and we're ready for the questions.
So hand back to Martin.
Great, thank you very much. A number of interesting ideas and concepts raised there. So we've already had some questions, but if anybody else would like to ask a question, please type it into the Q&A box on your screen, and we'll attempt to address as many relevant questions in the next few minutes or so. We have about 15 minutes available to us. So we've had a number of questions already. Somebody early on sent in a question asking, what is the average lifetime in years of high voltage batteries?
So this is not so easy to say, but from our experience and our calculations, it's something about 10 years.
But it depends on the SLC range, how old was the battery at the beginning. But yeah, 10 years it's our plan.
Okay, thank you. You mentioned early on in your presentation the lead acid battery technology, and then obviously we've switched now to lithium ion, and we're looking at other technologies in the future. Can you just talk about, you've underlined some of those points already, but what's the main benefits of lithium ion in comparison to lead acid batteries?
Yeah, this lead acid ban, also the state of charge. Normally you discharge the lead acid only to 50%. When you go down to 0%, it's from the durability not good. And lithium-ion technology, I think it's also now built in this vehicles. So in the next years, the customer go up with bigger batteries, and the old batteries come back to the OEM or the customer. And so you have at second use or second life concept, very many batteries you can put down to a stationary plant. And also you have economical advantages. So with rare materials, you can put them in this second life storage and have the opportunity in 10 years to go in recycling, that it's had an economical benefit.
All right, thank you. I wonder, do you envisage batteries being produced specifically for second life applications?
Sorry, can you?
So in other words, I was wondering if you envisage batteries being produced in such a way that they factor in that the batteries will be used for second life applications after they've been used in an electric vehicle.
So yes, like we know they are not produced for second life. Normally you have to consider that the battery normally is developed for the vehicle application, but it's not especially produced for second life application or stationary application. But it makes sense to have a look if you don't want to recycle it after maybe 7 or 10 years in a vehicle, it makes sense that you have that you consider what has to be done to reuse them in a second life. So yes, this is something that you have to take care of before developing it only for a vehicle. So I hope we get the question.
And I wonder, I guess this is more of a business model question, but do you envisage the second life being factored into the battery costing and pricing as a result?
Yes, this is an interesting question. So this is something that that our customers are considering, maybe the big car manufacturer, as a possible business case to resell the batteries, but not only as a second life. You can even think about using the car battery in a first life for stationary applications. So this can also be a business case that can reduce maybe the cost of the battery pack for the vehicles itself. So it can have a double impact on the costs. And this is something that our customers are evaluating for sure. Yes.
And are there sufficient examples of tried and tested industrial applications where batteries have been used in a second life application? I mean, if we think that the current round of electric vehicles came to market in 2010, we're talking about a battery life of 7 or so years. That only takes us to last year, really, before those batteries were considered to be ready for second life applications. How long do you think it is before we know whether they have performed sufficiently in that second life application?
So I think yes. Now the first second life batteries are available, but as you said, it's not really a big number because looking to Europe or even to US, maybe in China you have got a lot of batteries that can be used, but I think it will take another 3 to 5 years until we have really a lot of or more second life battery applications or second life battery systems. I think, as I know, we already have done some projects in this sector, and we will need another 5 to 8 years to see if they really perform like they should, because it's right now it's just a theoretical aspect that we have analyzed. So I think in the next 5 to 8 years, we should have good results, not only for second life, but even for first life, how automotive battery packs are working for stationary battery applications.
Okay, we've been talking, in my mind at least, mostly about passenger car batteries. Is there a difference between a passenger car battery and a heavy truck, a battery from an electrified heavy truck, when it comes to using it in a second life application? For example, the size of the battery, the capacity, and so on.
So normally, if you look to the module, it depends always on how the battery was designed. But a lot of heavy truck applications are not working on 400 voltage level, but they are already working on 800 voltage level. So this would be a big advantage if you want to use them in a second life, or let me say in a stationary battery application. But right now there are not so many heavy truck applied with batteries. But this is, like, I know it's one of the difference, because they are often working on another voltage. So this, like we said in our presentation, this can be a big advantage to use them in a stationary application, so you don't have to redesign all the components to see if the contactors are working or if the isolation is okay, but it's because it's already designed for 800 voltage. This is one thing, and maybe it depends now on what heavy trucks, maybe they have got other use cases, because the heavy trucks are normally running more than 5% a day. They have to run as much as possible to earn money, and so this is also something that you have to consider, because I think using a heavy truck battery has one big advantage, because you don't have to redesign so many components. from our opinion.
Okay, thank you. A lot of what we've been talking about today is a corporate business case. Sorry, I'm trying to get the words right here. Is a corporate business case where the corporation, in this case the vehicle manufacturer, would decide that the battery is now ready to be put into a second life application. Where does the customer come into this? How does the customer benefit from knowing that the vehicle that they use, the battery that's in that vehicle, will at some point go into a second life application?
So there can be different aspects. For example, the ecological aspect that you say that I want to drive a car which is almost up to 95 to 100% recyclable, but not only that you can also reuse a lot of parts. This can be a reason for the customer, even if maybe there can be an incentive for the customers if they want a new battery pack for their cars, that they get an incentive for the old one to use it in a stationary battery system, like for example Second Life. Another idea can be that the customer could use his own battery pack from his vehicle for his own stationary application, for example for his house or for his company maybe. So these are different ideas which are already discussed in our company, or even at the big companies like the OEMs, because this is a new business model, like you said, in advanced, and this could be an advantage, not only a cost impact for the customer, but even an advantage to have his own second life battery pack after his first life use in his electric car.
Thanks. It will be interesting to see how consumers get involved in this, because we're hearing more and more about batteries being used vehicle to grid, but also those batteries, we see them in proposed applications in domestic settings. So I think there's still some work to be done here.
Yes, sure. Yeah.
We've got a couple of minutes. I'm just looking for some questions that address areas we haven't already talked about. We talked earlier about the difference between lithium ion and forgive me, the traditional style of battery.
Yes, lead acid, okay.
Lead acid battery, yes. Somebody's asked a question about cooling here, active cooling, and whether there's a difference between the different types of batteries, lithium ion, and perhaps those that don't require cooling, such as solid state batteries.
Okay. So it depends a lot of. So normally you should use the same cooling concept, but it depends a lot of the technology and how the thermal setup of the cell is built up. So this is something which is really important to look on in the future, because it's quite new. This solid cells. So from our point of view, it depends on, you have to do some analysis, maybe some simulation to see how the thermal activity is inside the battery packs. You can look to stationary applications, either to as well as vehicle applications, and then you have to see if you have to redesign the cell cooling or the active cooling concept. Because, but normally from the procedure, it should be the same procedure. And the only thing you have to see if the cooling capacity of your system is enough, or maybe if you can reduce it because you've got lower thermal impact on the cells. So this is something you have to look once you have the new cell generation.
Thank you. We have a number of questions still. I'm going to try and get through a couple more if we can in the next minute or so that we have available to us. Yeah, here's an interesting question about tracking a battery from first to second life. The question here is asked whether there is any way that batteries can be tracked from first use to second life and beyond. And we've had some other questions about the warranty that would apply to the second life battery. So I wonder if you can sort of provide an answer that takes those two issues into account.
Okay, so let's start with the tracking. So there are different ideas you have to do specific tracking in the vehicle. So right now, I think not every battery or hybrid car or electric car has already all this different tracking. So you first of all you have to track how the battery was stressed in the first life, and this data should be always available inside your battery pack. To match them. This is another important topic. We didn't really discuss it, but to use a battery in a second life, you always have to see how was the battery pack stressed to match them together properly. So I think that will come a lot of data from the cars, and this data pack or this logic should be continued for stationary battery applications. So you don't have to track them. Really, which customer has the battery, because the important thing, how was the battery stressed, and this is something that can be continued also for second life. The warranty question is quite good. So it was, from our opinion, it was quite hard to have any warranties for your electric cars. For example, it's at least 100,000 kilometers or 8 years of use. Something similar will be done for stationary applications. From my ear, there's no officially really warranty right now, but they're saying if you use them in the right temperature range and the right operation strategy, it should last for 10 years using it 24/7. So you can have to look on the cycles that your battery is doing. This is another important topic, but this is interesting question whether OEMs have to find an answer if they want to sell the batteries as a second life. But it's quite a lot of work to do.
Okay, well, let's finish on a question about standards. You talked about certificate of conformity at the end of your presentation. So let's end this Q&A then with a question about standards. Will there be a standard for battery pack swapping, and has there been any interest from any particular OEMs in this?
Yes, there from our knowledge, there are I think all the OEMs. Let me say that one in Germany, also in France, they are quite interesting in having specific and let me say the same regulation for battery packs, for the stationary battery packs, like we showed in the presentation. For the CE, there are already existing regulations, but as we know, they are not specifically for stationary battery packs on this voltage range. So as we know, there are directives where different parts are working on, but I don't know exactly when they will be announced. But I think in the next one or 2 years, because some of them are already in draft modus. So I think that they will come in the next 1 or 2 years.
Excellent. Well, thank you both very much for sharing your insight today. We do have to draw this session to a close now, and I hope I've taken as many topics into the Q&A as possible. Thank you for fielding all of those questions. And thanks, of course, to everybody for joining us, and to FEV and EVA for making this event possible. There will be an opportunity to download slides as well as to access an on-demand recording. We'll send you an email to let you know how and when you can access those. And with that, I wish you a pleasant day. Thanks very much, and goodbye.